So we're looking at section 5.2, and the name of this section is the definite integral. And in section 5.1, what we did is we estimated area. And what we had was some function, and I'll call it f of x. And what we did is we made a series of rectangles to estimate the area underneath said curve. And we used a left-hand sum or a right-hand sum. And what I do want to talk about here is very quickly, if I'm going from A to B with, say, a left-hand sum, we can say that certainly, and let's use n rectangles, a left-hand sum with n rectangles, that the width of each rectangle, and I'm going to call that delta x, is equal to b minus a over n, right? B minus a, the total distance between them, and divide them by n because we have n rectangles of the same length. And then what did we do? We took that delta x and we multiplied it by the first height, f of a. And then we multiplied that by the next height, which was f of a plus delta x. Oh, I needed a delta x there as our width. And we had the next height, which was f of a plus 2 delta x times the width, until exhausted from our toils, we finished up our final rectangle. And if there are n total, and here I had 0, and then 1, and then 2, so it would be f of a plus n minus 1 times delta x, and our width was still delta x. Now, I don't really care about this term. What I do want to say is I'm going to factor these delta x's out. And I'm going to be left with this really long sum. F of a plus f of a plus delta x, all the way down to f of a plus n minus 1 delta x. And as much as I love this, I have shorthand notation for this, and this is called sigma notation. And, you know, the sigma notation is just fine. I'm just going to say I'm going to start out at I equals 0. And that's where I'm going to have my formula, which is going to be f of a plus I times delta x. And at the starting, I is 0. And so when I put a 0 in, that term zeroes out. And we just get f of a. And then we add the next term. Sigma means sum. And so I'm going to have the next one when I is 1. We'll have f of a plus 1 times delta x, and then f of a plus 2. And I'm going to have my terminal value is n minus 1. And the reason that I wanted to write this is that all of this inside the square bracket can be condensed to this. And I'm still going to have that delta x, which is the width. Now, this is not a part of our course, but it is important in going from here to where I want to go, the definite integral. And the definite integral is the exact area under the curve. From A to B. I guess I used lowercase before, so I'll use lowercase again. And so the exact area. So what am I going to do, friends? How am I going to get this idea of an estimate to an exact value? And you saw last time that the more I used, the more rectangles, the closer it got to the exact answer. And so what we'll do is I can take this sum, but instead of having n being some finite number, let's let n get really, really big. How am I going to do that? We'll take a limit as n goes to infinity. So here we'll go. We'll say that the exact area is the limit as n goes to infinity of this hot mess. I equals 0, n minus 1, f of a plus I delta x times delta x. And wouldn't you know it, we have shorthand for this. Now, we should say that as n goes to infinity, a couple things are going to happen. Delta x is going to get infinitesimally small. And instead of writing delta x, I'm going to write dx, this like infinitesimal change in x. And instead of sigma, I'm going to use the elongated s. I'm going to say, hey, I'm going to start at the lowest value, a, and go to the biggest value, b. And what am I going to be putting inside here? Oh, well, f of x. And so this sigma notation, when I take the limit as I go to infinity, I get this. And here we have the definite integral of a to b. Now, definite means it has a starting point and an ending point. Integral is this infinite sum, and what this is the exact area underneath a curve. So we understand that this integral from a to b of f of x dx is the exact area. But really, that's a slight lie. It's the exact signed area between f of x and the x-axis. And what I'd like to do is just one little example here. And we'll go and let's have this a, or that'll be 0, a, b, and c. Fine. And I'm going to let you know a couple things. I'm going to tell you that this area here, the area underneath the curve that I'm hashing out there, will be equal to 2. Let's say the area here is also equal to 2. But notice that it's below the x-axis. And let's have this area be equal to 11. Good. Let's call this f of x. And if I wanted the integral from 0 to 2 of f of x dx, and we have to have that dx because that is our infinitesimal width when I made the rectangles, we would want the exact signed area from 0 to a. That would be 0 to a, not 0 to 2, and that would be equal to 2. Let's go again. How about the integral from a to b of f of x dx? And sure, the area is 2, but that's not what we're interested in. I need the signed area, and so we're going to have negative 2. Similarly, if I was to go the integral from 0 to b of f of x dx, we would have a positive 2 and a negative 2, and so that total area would be 0. Let's go for a couple more. Let's go from 0 to c of f of x dx, and we'll see that I went positive 2, negative 2, so I've netted 0 here, and then I've gone up a total of 11. I've got one last question for us. I want the integral of 0 to c of the absolute value of f of x. Still having dx. And now we need to think a little bit because, this is positive, so the absolute value of that is going to be exactly 2. This is still positive, but what's going to happen, what we'll really have is this flipped version, and so the area here will be 2, and then 2 more, and then 11, giving us a joyous 15.